Before giving the floor to our experts, please let me share with you some bullet points. There is a well-known Moore law where the speed of data calculations decreases exponentially. But you can see that this diagram, the productivity of the system could be measured by several indicators. By some of them, several years ago, the highest ceiling was achieved several years ago. You could well see it from this diagram. For example, transistor size, microchip size, there is some progress, but if you carry on longer, that by 2020 we will reach the size of microchips as big or as small as one atom. What will happen then? Will there be an end of this process or not? When you see this slide, that across 100 years there was an exponential growth, irrespective of the fact that there have been changes in the technologies. There were lamps, and then came the transistors, and then microchips. There was growth. So the question is, what will happen tomorrow? Will there be a stoppage, or the progress will be there? So what we see today in terms of the computers, that we have semiconductor technologies in terms of hertz capacity, but you could use multi solutions. You could use as well as such things as graphene, for example, to attain better cleanness. On the other hand, if you want to increase the velocity of calculations, we might see several candidates, such as photons, plasmons. So, what is so good about that? The photons are 100,000 times more clean as the current velocity of calculations. So, if we're capable of managing photons, that's going to be a breakthrough. So, this is about what might happen. A physical solution of this technology is still to be achieved, is yet to be achieved. Another example, which could be discussed later today, maybe we could use a different logic without using a 0 and 1 logic calculations, but we could use quantum measures, for example, particles, which could be used in better to achieve a gigantic parallelism, arriving at a radically new solution. This is what we might be discussing today. You might be listening to very interesting speakers, which could pose a question, an open question. Do we really need fast calculations? So let's discuss these bullet points today. Pavel Lebetsis will be the first speaker to take the floor. President of Microsoft. Thank you, Ruslan. You sounded highly technological. I might be used as a white bird, where I would be touching base economics of the technologies, because we live in interrelated world. So I will be leaving aside highly technological discussions to the other speakers. So let me start with a context for discussion. A very interesting fact. The latest Harvard Group Symposium identified 10 largest technological trends which we could be witnessing today, an ongoing one. Most of these trends are well recognized. First of all, a universal use of computers everywhere, internet, connections of different things, and even people in some cases. Number 3 is so-called 3D printing, which gives us wonderful results. Where you would be listening today, big data analytics in the context system, smart devices. You might have two per person, maybe, this will, cloud calculations and mobile applications, which even in the Microsoft technologies could be found in very interesting and diverse applications. Infrastructure, web scale IT, and business loan safety and protection against computer threats. These are three major trends. So these very deep calculation capacities, which was touched base by Ruslan, are being used in all these trends. What I would like to share with you with three very simple economic bullet points. Number one, introduction of high-tech solutions, whether they are global or local or both, without any doubt has any impact on labor productivity throughout the world and throughout sectors. It affects the capacity of a country as a whole. Take a look at their small and medium-scale business, which is an indicator of an economic and technological progress in the marketplace. Most of small and medium-sized business should recognize that they are today just because they can use high-tech. Without high-tech capacities and opportunities, there'll be no business like this. For example, Boston Consulting Group carried out a study for small and medium-sized business, and this is their results. A high-tech business, which uses sophisticated solutions, 1.5 more sustainable than those businesses which don't use that technologies. 90% of such companies recognize that the high-tech factor is a very important thing for them. Two-thirds of such companies believe that this is a key factor for their success. Taking a look at the Russian marketplace, you could see that 15% of our economy accounts for small and mid-sized business. As compared to other countries, Russia is yet a long way to go. IT, human resources potential. You could find the same comparison table. Human resources share in GDP of Russia is 1.4%, while in Poland, 1.5 higher. Norway, 4 times higher. So you could see where high-tech is present in business, just in business. It's not a high-tech business as it is, and the way sectors develop on a national scale. So this is one finding of mine on. Another bullet point of mine is that attention, very important attention, given by the Russian government to the IT sector. We believe that this is a signal that this sector will have an important role and may make a difference in the economic development of the country. One of the issues, acute issues, facing this sector from the point of view of development and economic development as a catalyst for the IT development and high-tech is that we have a very big shortage of qualified IT human resources capacity. The figures we have yesterday, I heard quite a number of figures, is that Russia, we have about 350,000 software developers. In China, as a comparison, 4 million. The Russian government to attain a breakthrough development of this sector, we need at least a million software programmers and developers, 1.5 more. And this is directly related to the educational aspect and human resources capacity and development. As an example, Microsoft as a major player in Russia and one of the actors in this matter developed an IT educational program targeting different subsectors. We have a program for the students of high schools to attract kids. We have programs for the students of universities, helping them to develop their knowledge base. And we have a program to support startups. So you can see the entire portfolio of programs. We have a seed fund, which we distribute in a specific way, and we use some platforms well known to you to support startups. For example, Skull Cover project, fund of IT initiatives development, and some others. We try to contribute in some way to continue development of IT human resources. And the last bullet point of mine is that when we start discussing high-tech issues, one of them has been mentioned by Ruslan. We might be talking about myths. A software program is something very easy to write. Like rocket science is much more complicated. On the other hand, I would like to oppose that software programs very complicated, that they are as complex and complicated as rocket science. And there are some of the jokes that if, for example, if an aircraft is without wings, then you will have only IT technologies inside, nothing else. So these are very complex systems requiring huge investments, time resources, human resources, other resources. For example, Microsoft company, one company, spends $9 billion for research, R&D. This is a huge figure, which is very difficult to duplicate or replicate, because most of the companies spend much, much less. So this is really very complex, and they require qualified personnel. They're time-consuming, and they require time resources as well. Again, we try to cooperate. Here are a couple of examples. We have joint R&D center in Russia. One is for the Moscow University, another is in St. Petersburg, a third one is cooperation with other universities for IT development, targeting local solutions. For example, those are produced by national developers based on our technology and knowledge base. We help them to be successful. A success is something I would like to remind you is not only a success in a specific marketplace, but success which could be measured globally across the globe in different countries. One of the great examples of such cooperation, and we have quite a number of cooperation projects, is a very well-known cooperation project. Kaspersky Laboratory is a global brand, and this is a very good example of success on a global scale. So this is what I was going to share with you, just to make sure that you understand that high-tech is not high-tech, but also it's a very interesting and big economic space with a huge impact and influence on the national economy. Thank you. Thank you, Pavel. Really, IT sector development is a priority for this country. But coming back to future computer calculations, we know that Microsoft is a leader in software development. So what about your current and future products for the consumer market, for business? Would they require big data systems? Very good questions. I do believe that this is a very logical question. And here is a brief response. A few examples. We are one of the biggest companies, capacity builders. We spend huge amount of money and huge effort in this direction. We understand better than anyone else than what we call scientific calculations or computation requiring huge. This is tomorrow's commercial calculations and tomorrow's consumer services. So what was like decades ago was scientific research today found usage on the consumer market. Everyone uses it now and every day, and no one even gives a thought what kind of computational capacity it requires. We understand this, and when we started using iCloud computational technologies, we are leaders in terms of practical usage. We, of course, never thought that clouds would be used to manage cities or university campuses, or maybe to manage and govern hundreds or 10 millions, dozen millions devices. We never could even suspect that, but we believe that this is a very logical continuation of our efforts. Yes, thank you. I'd like to give the floor to Igor Kalashin, Director General, second leading company in IT. Igor, you are giving the floor, please.
So, the interesting that the name of the second company, a leader in the production of microelectronics, is shown here. So, now, well, Ruslan maybe was not very positive about the gigahertz ceiling, and we didn't see much of growth here, but we should also remember that we should think about the energy efficiency and general productivity of systems. So the processor productivity is calculated for the area it occupies, certainly increases multiply and generation by generation. And if we talk about the productivity, and the ratio between productivity, high performance, and against efficiency, then certainly it's growing generation by generation, and the production of processes shows a great progress, and it is confirmed by the Moore's law. And now the market features the products that were manufactured by 14 nanometer technologies, and well, they become smaller and smaller, go down to 7 nanometers and so on. And we should ask our researchers what would come next. So Intel, a few words about it. So where is our position in the world of high-performance calculations? Yes, certainly this is our priority, and there is a demand for the growth of the calculation capacities, and I will explain why. So what do we do? What we do as regards the content and the base platform for calculations. This is, first of all, a continuous improvement of the technological process, and we overrun the other companies here for a year or for 2 years even. So if talking about statistics, then the high performance systems for just 80% based on Intel platforms. So, and just not long ago, those systems that appeared not long ago were all built on Intel's platforms. So for data processing and calculations. So today in the morning, I read the last quarterly report on revenues of our company, and the volume of revenues in the data center group was $3.7 billion for a quarter, and the growth of percentage was 16%. So the 16%, while in terms of domination of Intel in this area, were gained due to not due to the share of our competitors, but due to the demand, which that demonstrates constant growth. I want to explain why, in my opinion, it grows at this pace. Well, there are a few interesting statistics. For each 100 to 200 smartphones in the market, one server is bought, high-performance server, for data processing and storage, including social networks and so on. So it should be calculated, it should be multiplied by the number of smartphones available on the internet, and we'll see the giant growth. So in the internet, so we have devices that communicate between each other via the internet, and we have about 50 billion devices of this sort, and they are constantly growing in number, and we will see 212 billion such devices in a few years. So, and revenue here will be equal to about $3 to $3 trillion. Because now we have 50 devices like this, and we'll soon see more than 200 of them in use. So, and they all need data processing, data storage. Certain analysis will be needed of these devices and their interaction. Well, another interesting fact. Well, by Gartner assessments, by 2012, 50% of all solutions and devices in the area of Internet Things will be produced by startups not more than 3 years old. So you should just imagine the existing niche and the existing potential for Russian startups in this area. So here, so we talk a lot about import substitution, and I think that it is an economic demand, but it is even more important to my mind to occupy a certain niche in the international market, and this potential is available with our startups. So some sort of export domination, or at least to gain our own share of the market in the field. So, and our company helps such startups all over the world. We have special platforms to encourage makers and enthusiasts to get the market access for their new devices on the basis of Intel Galileo and Aegis platforms. So we carry out competitions for portable devices, wearable devices, and we attempt to vigorously encourage such enthusiasts to fuel them up and to provide a technological basis for their businesses. And just a few words about some trends. So where all this data is processed? It is processed by data processing centers. So there are certain criteria of to such centers. First of all, this is a high speed of setting up. Then the ownership value, simplicity in the management, and so on and so forth. And certainly the price. And to satisfy all these parameters, we just should follow the trend in using so-called program-defined infrastructures or software-defining infrastructures. So if we used to see data centers, the data centers were kind of zoos with different devices that are physically managed by people while just working with different wires and plugs. So now just today these functions are implemented by software, and actually all data processing is implemented by machines. So we do everything virtually. So if we look further, we'll look to the evolution of such data processing centers and what can be done here. So above these criteria and parameters, one very essential element should be added. So these software-defining infrastructures cannot exist without the program-defining security. So when we do all we can to work with them to maximize security of the most critical nodes. And so just in addition to virtual appliances and security appliances, intrusion prevention systems and firewalls, so everything transfers to the virtual world. Intel Security Control, a platform, was introduced not long ago, and it allows to transfer this virtual solution to machines and to ensure the security and safety of the data processing center operations. So Igor, we heard that Microsoft, first of all, deals with the hardware, and you, Igor, mentioned that the most of the supercomputers were built on the Intel processor solutions. So I know these are big clusters with dozens or thousands of processors. So and certainly software plays a key role here. So what is the attitude of your company to software? And maybe you would propose some new parallel solutions. So certainly it is a key aspect in our work, and we need parallelization because we need more nuclei, we need more systems, and I don't think that Intel alone can just turn this world upside down and teach and learn each developer to use the right code and the right processor capacity. So we supply high-quality building blocks for a developer to implement such technologies at higher speeds. For a cluster classical calculations, we provide BI libraries. If we talk about just ordinary developers for software, they can use Intel compilators to activate the code. The others use libraries, mass kernel libraries, for example, which already have been optimized with high quality. So we provide all this scope of building blocks that could serve as a base for your solutions. So these parallel directions of calculations with multiple nuclei, is it promising? Yes, certainly it shows promise. Of course. So we heard that the giant aspect was related with processing of big data, and to process this data, we need to store and transfer this data. So I would like to give the floor to Bob Plumbridge, a technical director for Europe, Middle East, and Africa, of the Hitachi Data Systems. Bob, you're welcome.
Thank you, and turn this off. Thank you, and good afternoon, everyone. I'm Bob Plumbridge, the CTO for Hitachi Data Systems in EMEA. I'm not sure how we move the slides forward. Okay. Thank you. So this is me. I'm also chairman of the board currently for the Storage Network and Industry Association in EMEA. Our prime role at SNIA is the development of standards for a lot of the technologies we've previously heard about and some of the things I'm going to talk about. Standards play an increasingly important role in my view. Technology is now changing faster than it's ever changed before. As you see there, I've been involved in the industry for over 30 years. I've seen more change in the last 3 than I saw in the previous 20. And I expect to see more change in the next 2 than I've seen in the previous 5. There is no end to the technology developments across the entire computer space, whether that's individual devices that we use or whether it's the very large-scale computing that a lot of very big industries use. The developments are staggering. One of the problems of such quick development is that our customer base are finding it increasingly difficult to keep up with that change. Whenever they make a decision on new technology, that decision is likely to be obsolete within 18 months. That creates huge problems for our customers and end users. Just keeping up with this is a complete nightmare for everybody. And consequently, what you see is organizations skipping generations of technology. And we see that on a regular basis now. Organizations just saying, we're too far down the line, we're going to wait for whatever comes next, and we're going to suffer the business consequence of making that decision. So this is a very different model to what we saw even 5 years ago. And as I say, this is not going to stop. If you look at our business has changed dramatically over the last 5 years. Regards the information solutions part now, that's really where the concentration is. We were known as an infrastructure company. We're increasingly being known as a data manipulation and a big data company, a company that now runs the analytics on the data that organizations are storing. And one of the other interesting points there is that the length of time that organizations are keeping data for has increased exponentially, just as the quantity of data that organizations are storing has increased. To give you one brief example, finance organizations across most of Europe were required to keep most transactional data for 3 years. They're now required to keep it for 10 years. That's a 3-fold increase overnight in the amount of data they store. And of course, at the same time, they're increasing the quantity of data that they store on every single one of us. I don't know if we're going to have time today to talk about privacy issues, but when you start talking about big data and big data manipulation, privacy is a huge concern for almost everybody involved, because big data is not just going to affect every business, it's going to affect every single individual in this room, and eventually it will affect every single individual in the world. That is going to be the impact of big data over the next 3 or 4 years. The scale of it is immense. If you look at healthcare, healthcare in the UK now requires that all digital healthcare records are kept for the length of life of the patient plus 5 years. So if I live to be 80, they're going to keep my data, my medical records, for 85 years. Sounds easy, doesn't it? Except when you consider that the storage industry has only existed for 60. So we're now openly talking about keeping data for longer than the storage industry has existed for. Nobody has ever done this before. And yet most people seem to think that this will just happen without any problems. Well, I'm very sorry, it won't. Will be a lot of technical challenges along the way to do this, not just in terms in the way of the data stored, but also the applications. Can anyone here tell me an application that existed 60 years ago that still exists today? I don't know any. And if you bring that more up to date and you think about products that were in common use even 20 years ago, things like Lotus 123, WordPerfect, they were all in common use 20 years ago, obsolete today, disappeared. Data that was stored in that format even 20 years ago today is completely obsolete and is largely unusable. And the next 80 years will be no different. And as I've already said, the pace of change will accelerate. It will not stand still. So these are huge problems for the industry and for our end users. And hopefully we'll get a bit of time to talk about a bit more about this. Also, the type of data we store, why it's being stored is changing. Economic situation that we've had across most of the world with the economic downturn has driven a lot of this change. Globalization, most organizations now wanting to work across the whole planet, want to be able to share data in every market with every other market. Again, it sounds easy, but actually it's quite difficult to do still, and still quite difficult to do on a reliable and consistent basis. And organizations are already running into issues with this. Huge number of new rules and regulations about data privacy. As you may know now in the EU countries, the idea of the right to be forgotten has now been enacted. What that means is, to give you a practical example, is I could go to Google and say to Google, you must delete every single piece of information that you hold on me as an individual. And Google must put in writing that they've complied with that request. I tell you now, that is technically impossible. You can delete data out of primary systems in seconds. The average organization has 8 copies of every single piece of data they hold. There is no cross-reference from those primary copies to the archive copies, to the backup copies, to the test copies. They have no way of deleting that data. So some of these regulations that are being passed into law technically are impossible to comply with even today. And yet most people believe this has happened and everything's working as designed. Well, again, I'm afraid it's not. There's a huge amount of work needs to be done in order to be able to comply with this. Mobility, another huge area of development. Every single one of us in this room, I would imagine, has at least 2 devices that connects to the internet. And I think one of the previous speakers mentioned that by 2020, we believe we'll have 50 billion devices connected to the internet. Every single one of those devices will be generating data that will be stored, and that data will be stored for very long periods of time. What do you do with the data? How do we use that data for the greater good? These are some of the questions, I think, that hopefully we'll get more time to explore. So big data, huge, and the majority of this data is now being generated by machines, not by us as individuals. And this is where this exponential growth is coming from. To give you a scale of this, quick example, New York Stock Exchange, very traditional business, been around for a very long period of time, do about 3 billion share trades a day. That generates about 1 terabyte of data. So in the grand scheme of things, relatively small by today's standards. Twitter, and these numbers are probably out of date now because these were done a couple of months ago, 645 million users, 700 million tweets a day, generating 20 times more data than the New York Stock Exchange. Let's look at machines. What machines are generating already completely dwarfs those numbers. aeroplanes. These numbers were taken from a presentation given by the CIO at Lufthansa. They now monitor real-time all of the fuel consumption numbers coming off of all of their aeroplanes while they're in the air. 5 years' time, he believes black boxes on aeroplanes will be obsolete because we will be streaming so much data real-time that we can analyze real-time to the ground that dwarfs anything we could ever store on black boxes in aeroplanes. And of course, the big advantage here is the black box, unfortunately, sometimes can't be found. If you're streaming the data real-time to the ground, there's nothing physical to be found. You already have the data, and you can run real-time analytics on that data. So there's even a possibility here that you can actually prevent crashes rather than find out afterwards what caused a crash. So we're moving from a reactive world to a proactive world. So again, a huge change. And then, of course, there's the extreme examples of research telescopes and obviously things like the Large Hadron Collider at CERN, which are producing data that even dwarfs anything that aeroplanes are currently generating. So hopefully what I've been able to do there is very quickly give you an overview of perhaps the more commercial elements as we see them and some of the challenges that we currently see in today's market. And again, maybe we'll get a chance to talk a bit more about how we see this developing over the next 4 or 5 years. So thank you.
Спасибо, Bob.
Thank you, Rob. A very interesting question. Suppose we build high-capacity data centers. One potential narrow point will be in the storage, because we'll have so much data that there'll be a storage issue rather than a data management issue. What do you think about that? Очень важный момент вы затронули.
Sorry. There was a research paper done earlier this year that forecast if we continue with the rate of growth of data storage that we've seen over the last 5 years, the data storage devices will be consuming the entire world's electricity supply. So you're right. The current way we're doing things is not practical long term. We have to move to a model where we can do the real-time analytics, where we can do when we're streaming the data, we know what data to store and what data to discard. And the Large Hadron Collider at CERN is a good example of that, because currently approximately 80% of the data they generate is never stored. Now, I know at CERN they're looking for very specific things within the data, but the belief is that if we can do that with that type of application, then there will be the ability to move that into a more commercial environment in the future. But again, a huge amount of R&D needs to be done in this area.
Thank you, Bob.
Thank you, Bob. We maybe pose the question in this way. Managing data, thinking about algorithms, and we have here one speaker, Wolfgang Hildesheim, who is market sales director of the company I mentioned.
A few words about this.
Yes, thank you. So my name is Wolfgang Hildesheim, and I'm running the Watson business of IBM in Europe, in Middle East and Africa, and I want to present to you the topic Watson. May I ask you the question, who in the room already heard about Watson? Please raise your hand. So then I will talk about Watson. Every 15 years, IBM is creating what we call a great challenge. And 15 years ago, the great challenge was, let's build a computer who can play chess. And you all remember IBM built a computer called Big Blue, and nobody believed that world champion Kasparov at that time could be beaten. So they played several matches, and Big Blue actually beat it. Kasparov, and so this was a big challenge. And later on, the chess computers were commercialized, and today you can buy a chess computer for several $100 and very strong computers. So now the next grand challenge was that we were thinking what could be the next real big problem we want to solve, and where we really think it can change the planet. It is very exciting and very difficult. Maybe we can make it, we can't make it. And we were thinking, what about to build a computer who can read and speak like a human being? So a cognitive computer. And this is actually the paradigm I want to talk about, the cognitive paradigm. And the people said, oh, that's probably too difficult. And so how can we test it? And there's a game in television called Jeopardy. Who in the room knows Jeopardy? Please raise your hand. Yeah, so we built a computer, and the computer, actually it's a software algorithm, and Watson actually played Jeopardy and were winning 3 years ago against the 2 world champions on Jeopardy on television. And it's a quiz on television, so the people are asked on all topics on culture, sport, pop music, and you can make plays with words, be ironic. So it's a very difficult play. I wouldn't be able to answer, for instance, most of the questions. And Watson won this. And now what IBM then took as a next step, that we are now industrializing the Watson software technology for the different industries. For instance, for banking industry, for oil and gas industry, for the car industry. And we bring this capability to read and speak in the different industries. And this is a very exciting topic, and I see in a lot of industries and big companies, the people believe that this will be the next step. It will change dramatically the way how we work, and it will really change the way how we deal with all the data. And all the speakers before explained how much data there is out, and nobody will ever be able to read all these documents. Like the colleague from Hitachi said, in the UK there is, for instance, an electronic record of every person, and sometimes it's 500, 600 pages long, and you never can't read it. So Watson is able to read this in a second and can tell the doctor, look, this person has a diagnosed cancer. And this is why one of the first solutions we built, and you can find videos in YouTube on it. You type in Watson in YouTube, and first Jeopardy, then you see how Watson is winning Jeopardy, and then in the next you type in Oncology Advisor, and you will see one of the first typical Watson applications we built. It's a system talking about cancer. And there are 2 hospitals, and they want to be the world-leading hospitals in cancer research, and MD Anderson, Sloan Kettering Cancer Center, and their top doctors now use the Watson system to learn and work in a more efficient way in cancer research. So the ambition of IBM is not like for instance Apple with Siri, so that you talk in your iPhone, a consumer application. The ambition is to teach to the systems to talk about, for instance, English language, medical language, cancer language, breast cancer, and then read all publications of all time of all people on this topic, and that the software can then really interact with you and reading this for you, and you will be much more efficient. So the value of this new technology is unlimited. It's really exciting. So there are very straightforward improvements, like you will find information quicker. You will have higher quality results of what you find. You will learn instead of searching. You will learn instead of searching. You will find things you have not looked for. So it's a fully different way to work with it. And this is why I'm, for instance, from Germany. What I see in the industrial utility industries, cars industry, where they have huge call center, huge service center, or a lot of material around, for instance, Mercedes, 1,000 different types of cars, and it's impossible to read this for a person anymore. And now Watson can read this and advise to this call center agent what actually he needs to look at. So you call, I'm here, I have a problem in the street of Moscow, and he sees this person has an E-Class Mercedes, and immediately you see only E-Class Mercedes and then typical E-Class Mercedes problems, and that can help. So for best practice management, call centers, research, Watson has now ready to deploy solutions and is using this ability to read and speak. So you can look at YouTube, where you find more examples how the look and feel is, where we do the first projects, like in healthcare and the other industries, and that's exciting time and a new paradigm.
Спасибо. Как вы считаете, Вольфганг, если...
What do you think, Wolfgang, if, for example, each of us in the very near future would have an assistant like yours, would it require an exponential growth in their data management, data processing? I mean, do you think there might be an additional risk in this respect? What do you think?
No, I think that the most important issue here is that you have to work in a more intelligent way. So, for instance, we will need to develop more language skills. So in IT, this is called ontologies, or we will be able to develop libraries, semantic libraries on synonyms, and it starts with very easy problems that, for instance, you have water, Wasser, de l'eau, H2O, all, so the software knows all this is water. So big deal in pharma, for instance. And then you have like a children book on animals. So then your child can talk about animals, and you are proud that your son knows now this is a horse. And now Watson, you need to teach to Watson to talk, for instance, about in Russia oil and a particular problem on pipelines. So you need to teach to Watson the language of oil pipelines. So this is actually the greatest challenge. It's not too much about data processing and storage, because there's already today enough data out, and you need to start to unlock the value of this data.
Спасибо. Очень интересно.
Thank you. Very interesting direction you're taking. If we come back to data processing, velocity of data processing and management, I'd like to give floor to Vyacheslav Ilyin, who is head of the modeling department in Kurchatov Institute. And from the point of view of physics, Vyacheslav could tell us very interesting things about the future of supercomputers or alternative computational areas.
I will talk mostly about computing. So the main points mentioned by Ruslan just was were all around computing. So all tomorrow's computing. Tomorrow's computing. That's the main point of my talk today. I would like also highlight the following an alternative: parallel computing versus consecutive computing. So this is the scientific basis. Is a mathematical model and a consecutive implementation of operations. Well, as regards the problems or the tasks, for instance, weather forecast, we need to just to unlock these two problems, these two tasks, to make them non-parallel, or in other words, to solve this problem using various processes in parallel at the same time. So this is an example of weather forecast. All existing technologies take only one small step ahead. This is an analogy with a theory of perturbation. When we need to calculate some basic values and then make some corrections, and through that we can find out some non-trivial phenomenon in physics. So all values that are measured by the Hadron Collider are measured, but there are quite a lot of effects. For instance, the mass of a lot of elementary particles, ions and baryons, cannot be calculated through that. Here we also have a lot of tasks and problems that cannot be solved using a consecutive basis, consecutive method-based computers. So there are problems of exponential complexity or even higher, and of trivial complexity. So these trivial problems can be solved using today's computers, but as regards exponential complexity computers, very soon we see a threshold, and some problems cannot be solved. For instance, the decomposition of the a digit into simple digits, and it is the basis of cryptographic schemes. Cannot be solved using, just common computers which we have today. We know an example of a true parallel computing. It's our brain. A child or even a baby, 1 month old, can recognize faces easily. So it's a typical task of image recognition, but it is very hard. But it is hardly solved using modern computers. So here we can say we don't know how our brain functions because there are no digits, no algorithm, how it computes, how it does computing. So this is a challenge to all of us, and first of all to scientists. So quantum computing, it's a new paradigm, and here we use quantum processes instead of classical algorithms. And our giant parallel here emerges here. Here I would like to remind you of analog calculations, and the approach is actually the same, and it's been known for many years, dozens of years, where no digits and algorithms are used. An example, in the early 60s in the Soviet Union, the S-75 complex anti-missile complex was invented, and the special calculations were used for that, for some geometrical parameters. And analog computing was used for that. And today, we use digital equipment to calculate the Taylor's sequence, and some parallel approaches are used. At that time, we used just a very simple analog equipment, and it was efficient. Quantum computing promises a lot. For instance, as regards Shor's algorithm. Такой шум, ужас в ушах. So maybe it's quantum rain? So Shor's algorithms was proposed to solve a problem for the composition of a simple digit to 2 multipliers. It is an exponential complexity problem, and it is impossible to solve it using modern computers, but quantum algorithm allows reducing this problem to the trivial complexity problem, and if we solve this problem, it will be a breakthrough in cryptography. Well, I think that the next presenter will talk about the some quantum aspects, but I would like to single out that the quantum computer should be designed for each problem, should be customized for each problem. So maybe the quantum computing is in its just in its early stage, and we don't know how to approach a lot of things in this. But I'm not sure. So algorithm Shor is one of the examples here. So, and the exponential complexity is exchanged for a quantum process. And this quantum process cannot occur just immediately. We need to implement quantum processing and a lot of classic manipulations with lasers, ionic lasers or photon lasers. I've never seen somebody to develop such science as the assessment of performance of this part of quantum algorithms. And talking about parallelization, here I would like to emphasize that there is another paradigm. It's distributed computing. It's been evolved for many years, for dozens of years, while clouds were mentioned, for instance, today. So this is computing via the internet. And technologically, three dots, iGrids, clouds, while Google and Yandex use web computing. It's not just search or mass search. A lot of calculations are done at the same time in the overall web. During the search, these are very interesting algorithms and a huge step forward. So what comes next? I would like to mention that, more and more understanding comes regarding challenges and applied problems, which are perceived as an opportunity to use different computational systems with very high performance. For instance, big data concept, which is very popular all over the world today. So there we can discuss this for many sides, and for one of the sides is a kind of sort of social challenge. So any individual can be surrounded by a multiple number of computing devices. Well, we cannot translate computing into Russian. We use just computing because we use calculations in Russia for both. And in English, we use computing and calculations. And I think that the computing should be used officially in Russian. Because we need to delineate computing and calculating. So what can be, just invented for our everyday life, for the economic activities? So just the hardware, well, can do a lot. Why? How to manage all this? What should we do with this huge flow of data? I would like to give an example, which is being discussed a lot in Russia. It is a medical software, remote health monitoring. So there are quite a lot of patients that wear different devices, even built-in devices with a lot of sensors and sensoring technologies, analytical technologies, and we need, huge hardware which is to be transported, and the data should be stored for a long time, and during the data transportation and storage, we need to analyze them. Or just roughly saying that you will have a heart attack, just push the red button and wait for an ambulance to carry you away to the emergency ward. So during 10 years, we need to store this data. It is and it is measured in exabytes. So big data, a big data concept. It's a very interesting picture. Look at different circles that show different data volumes. And on the right, the physics of high energies and experiment atlas for 1 million files transported during a day. Today, it is about 160 gigabytes, and next year it will grow fast. So the data volume is given in comparison with the Google search, with Facebook. Here, big data was present always in the physics of high energies. Since the 60s, we worked with big data and we analyzed it. So it's a kind of advertising of our project. We start it on an international basis. It's a mega band. And the point is, that we need to have a kind of a federation-based heterogeneous services and resources through combining or uniting the management of data and calculations. That's it. Thank you. Thank you very much, Vyacheslav. I would like to introduce our last speaker, my colleague Alexei Ustinov. He is professor of ICT Karlsruhe and also head the scientific team in the Russian Quantum Center. Vyacheslav, I think that everyone is interested in quantum computing. Well, now you may have a look at how it's done, just in everyday life. And Alexei Ustinov actually implements this concept of quantum computing in hardware design. Thank you, Ruslan. I think that we've expanded the topic a little bit, and what we discussed before, it was a computer of tomorrow, and I would like to touch upon a computer of the day after tomorrow.
So the first demonstration example is here today, and you could buy those technologies. In fact, the area I'm engaged in is rather focusing on specific applications of quantum computers. It's not the only way to move forward, but you must understand why it is here, quantum. You heard it from the previous speakers that physics assistance will be required when you go beyond 7 nanometers, because you would put less than 100 atoms. You will find specifically different areas of elements. Here, we would be talking about new technologies which are not that traditional. For example, I'll go faster through my slides. Here we would be talking about the following. One needs to build quantum objects to be managed and could be scaled. We could build many of them, and we could use them to build devices. These quantum technologies, they are reversible, and quantum computers are a smaller part of reversible computers to reduce energy consumption, which is a big issue in current computation systems. These are not discretionary solutions. In this case, we are not talking about 0 and 1 error up. We are talking about a superposition when you could impose them on each other, quantum bit on quantum qubit, which is a sum of 0 and 1, where you would put the sum, taking consideration using different directions, because you would drive you would manage the movement of those arrows. In this technology, you would have many quantum objects to be used, photons, atoms, ions, and each of these technologies has strong and weak points. Photons are very useful for communication, but they are very difficult to link. Atoms are concurrentum, but it's very difficult to scale. So a technology which is a breakthrough is superconducting technologies. Very briefly, here is what it is. A picture which is made electronically. You could see a structure several microns big. The intersection of arrows, you could see films of superconduction. Schematically, this is a ring of which is interrupted by 3 objects which are super capacitors. The condition of this ring is as follows. You could go around the clock and against the clock. You could use these systems simultaneously. This is how you could build a quantum bit. We were in a position to measure them a year ago, 12 months ago, together with the Moscow University of Steel and allies. These devices could be made of films and metals with unique capacities. The superconductor has no resistance. You could cool it down to very, very low temperature. You could use refrigerators. Such refrigerators could be used. You could buy them. You could use them off shelves. And since you have a very low temperature, is not a limitation. 150 years ago, no one thought that we would be using refrigerators. Everyone used ice or kept their products in a cellar. Now refrigerators are very cheap and everyone uses them. So maybe sometimes from now we will be using a small refrigerator, very, very low temperature in an office. There is a technology like this, and it could be further developed later on, because right now only researchers using this technology. So we need to cool down the superconductor to a very, very low temperature, and in this condition it could be used to separate various components through a gap. The ring current will have no resistance at all and will be endless. So there'll be no loss of energy in this object. So we're using two different directions of the current, and these conditions could exist for some time. But then the system will forget when it was established like this. So I use this system, which I'm showing you in a diagram, and this is a summary of the conditions of superconductive quantum bits for the last 15 years. It's not that the structure diminishes or the frequency is on increase, but the coagulating time grows, and this growth for the last 15 years have been as big as 1 million times. The latest qubit, which was opened in '99, and it showed coherence. No one could believe it. Even I didn't believe that it was possible. So this time, when we could measure this time, this period, nanosecond, 1 trillion part of a second, is now, we could use it up to 1 millisecond. Why it is that important? Quantum bit should live as long as a period of one operation. If it could live 100 times more than one operation, then the amount of mistakes would be much less to use it as a real device. This condition could be used with the help of a special algorithm, and people are now creating it. One example. You could find it in Google or somewhere else, like typing quantum computer. You could find that there is a computer there. There is a Canadian company which started working on that 12 years ago. They made a statement that they made two computers like this, 2 generations. And the latest one is 1,000 qubits, 100 of them is in operation. The problem here is that having made this product, the company cannot prove that the process which is there is a quantum-based one. They demonstrated one aspect for the processor with 8-bit. So the question is that whether it could be used or not in major systems with major qubits is a complex question. It's an open one. There are proponents and opponents of such an approach. This is a hot topic of discussion. This computer is based on a very interesting principle. It is anabiotic quantum computers, which could see visuals. This company says that they addressed a very useful problem where they could use biotechnological issues by selecting parallel methods of computation. So we have a breakthrough, and the breakthrough is as follows. This year, Nature published a statement of one of the scientists that they were able to ensure sustainability and reliability of a number of operations, which is a dozen times higher than the quantum computations of the previous years. So this reliability is over 99%, is required to realize, to implement a separate coding of information in many resonators of superconductors on the computer chip surface. And this technology was demonstrated on a very small amount of qubit, 5 only, but there is great hope that our further steps, brute force scaling, could be used in a very direct way, and it's possible. Another great news is that a group which made this breakthrough possible, this is a leading group in quantum computation, it was hired by Google, which also bought this quantum computer for the Canadian company for $10 million. Google made a statement that they intend to new quantum technologies, but this is not new. Here we have several approaches which have a great hope in the near future. We need to identify how useful these computers are from the point of a consumer or maybe from a business user. It's not for tomorrow, it's for day after tomorrow, but this is a very intriguing technology which is progressing very fast. And here, Russia, we are doing it in a special center chaired by Mr. Yunusov, president of this discussion. I do believe that this is the one which I leave for your attention. Thank you, Alexei. Wolfgang wanted to comment on your speakers.
So thank you for the honor to comment here. I used to work as a particle physicist before I worked at IBM, so I was excited to see that in most of the presentations we had comments on particle physics, whether it's in a new paradigm with quantum physics or parallel computing or high data volumes. And it's true, right now the 160 petabyte you talked, the most important challenge is to get value out of the data. So to store data, find data, that is one side, but the most important thing is actually to get value out of your data. And the physicists at CERN and the Russian researchers at CERN are doing it through a trigger system. So they really reduce the data by different level. Trigger system 1 from 160 petabyte to let's say 16 petabytes, and trigger level 2, 16 petabytes to 100 gigabytes, 100 gigabytes down to so that they reduce it. And in the end, what they want to find is one really interesting collision of the Higgs particle. And in the last days, the Nobel Prize went out, and you will see in the next years, the next Nobel Prize in physics will go to the discovery of the Higgs particle at CERN, where they were able to reduce 160 petabyte to the one interesting one. And I think this is a challenge for all of us in the computer industry, to reduce data to something which makes value, is interesting, makes fun. So, and that's why I think I'm happy to work in the industry.
Спасибо.
Thank you. Before we wrap up, we have a couple of more minutes to run the questions and answer session. So welcome. Well, no more questions. One question is how this quantum computer operates. It's a question to Alexei. So, what's the structure? These circles measure current, and then we measure, and it goes into a specific condition, or what? How to store data if, for example, it is in such a state there. So, what is the way it works actually? This is an interesting question. It requires a very lengthy discussion. A quantum computation could be represented as this. When it is there in two conditions, it develops in a very predictable way. We established a condition which goes from 0 to 1 with a measurable speed. And this development in time, we need to cache and follow it without destroying it. So we have methods for measuring this condition, indestructible methods of to actually read the quantum condition. But any way to read it, you could destroy it. So during the computation, the condition will stay the way it is, and you need not to touch it. But you need to touch it when you want to read it. I haven't mentioned it, but computation is possible only when you have not one quantum bit, which is developing in time, but when you have several quantum bits which starts correlating with each other, and we have a totally different computational environment. Unfortunately, I cannot say more than what I am telling you now. We could talk after the session. One more comment. If you have time, I could. The Shor algorithm is supposed to do that. This is a deposition of a single number into two. And it's a classical solution using mathematics by a discretion mathematics system. First of all, you need to build a discretionary function. You could manipulate it, and then you come to a quantum process. You need to write function into n qubits. Well, I don't know how to explain it to you, but you need to write it down, to record it, a discretion function. I'm simplifying things in a very, very simple way, and this function should be recorded as a very logical operation, n plus n. There are many of them. Each operation could be realized. For example, catching ions into a magnetic catcher, and then you record them as n qubits, and then you use laser with a special light without destroying the quantum condition. And that's a starting point. Then a special combination of laser impulses. Well, it's not yet done, but it's going to be done. So these logical operations are being implemented. As a result, this condition will be as a condition where this function has been recorded. As a physicist, we then do measurements. They could be observed, and it is as close as I can come to giving you this response. You arrive at a specific condition, and of course we understand what kind of condition it is, and then you start checking it for an answer, deciphering very simple numbers, multiplying it by then the correct answer or not, and then we repeat the process all over again. So this is the way it could be done, approximately. Like it's a very simplified approach. Thank you very much, Vyacheslav. Very brief addition.
It was realized in two platforms. First in the NMR technology using an ensemble of chloroform molecules, and then it was repeated on circulate qubits. And two co-multipliers were obtained, OH as a product give 15, not much. Thank you. So all around talk about Shor's algorithm. Yes, certainly it is very cool to decompose 15, but if we increase capacity up to 1,000 qubits, then we can work with all crypto protection. And so one of the question, maybe such quantum computer is already in existence, and somebody already is overhearing us. Well, certainly, I don't seek for an answer from you, but we would like to take questions from the floor. Good afternoon. You mentioned different efficiency measures, energy efficiency, including and we did in physics and dealing with a certain heat release. Theoreticals developed a certain technology, such as. Do you know anything about developments in this area? Dealing with heat release, while energy efficiency was mentioned by Igor Kalashin. Maybe he would take this question. No, I work much more with software. I'm not a physicist, actually, and maybe some other people would help. There are other people who would like to answer something. So I will a short comment. So our brain is a kind of a computer. What is capacity of this computer when it's in operation? So when a human is thinking intensively, so we can certainly connect it to an electron. And 100-watt lamp would light up. So just, for instance, let's take another example with a baby. A baby recognizes mother's face. So here we have watts and the computer megabytes. So there are quite a lot of room for the optimization. So it was really exciting to listen to you, especially about the data storage and transportation that is developing, this area is developing immensely. Is there any margin, any threshold to which the information would reach a certain margin, and it won't be possible for us to store and to process this big data. So the overall discussion was around this. So if there is such a limit or not, and we will try to find the answer to this question. I would like to give a short comment to that. Maybe our colleagues from Hitachi would also add something to that. So, and here a limit is a cost, first of all, and there are quite a lot of data accumulated. And at one of the previous conferences, I heard that today more than 97 or 98% of data are not processed. They are available but not processed. So, yes, we can have computers of high capacity, but why? We need a certain business reasoning for that. We need the result here. So electricity, for instance, is rather expensive, and so on. So already today we have approached a certain limit, and where we have data to process, but we don't have reasonable tools for that. Thank you. Well, basically, we are running short of time now, and today's discussion is very optimistic, and we see to the end. We see our way forward, and we don't think that there is a certain limit to it, and our society moves to the information phase more and more, and we work not only with current process while processing data in our personal devices, and smartphones have more and more sensors, and sensors would generate more and more data, and so there will be a kind of avalanche growth of information in this world. But our experts are quite optimistic about the situation, and so it is manageable. So maybe someone would like for 10 or 15 seconds say a few words to wrap up. The humanity have so far coped with all challenges, and we hope that this trend would continue. Pavel, maybe you would say a few words.
Throughout my career, I've heard that there are limits to everything every 5 years, and 5 years later those limits are history. We've heard it with capacity. You know, we've moved from megabytes to gigabytes to terabytes to petabytes, and we're still moving now into the era of exabytes. So I'm always very skeptical when anybody tells me there's a limit to anything these days, because almost every limit I've seen has been blown away eventually. And certainly from what we see in our own R&D labs, when we look at increasing capacity of device, when we look at increasing performance, it's almost that there is no end to it. And we as humans seem to come up with a new solution to a problem eventually. And certainly from my experience, I don't think that's going to change.
Thank you, Bob.
Pavel started saying something. I would like just to agree with my associates that there is hardly a limit to this process. Well, but though the limits that might be are somehow predefined, pre-identified by our business and by our private life, so there are quite a lot of things that are technologically feasible, but we still don't know if we need them or not. And I think this is kind of limit. I would like to extend my thanks to all participants of our discussion, to all attendees, and I think that next year, if we meet again, I think that we'll have new data and some interesting topics to discuss. See you. Bye.